Are we live?
You're live
Yes,
now.
maybe
Sorry.
we are.
You're live now.
Okay, sorry. Okay, it is my great pleasure to introduce Yonghong Tian. Yonghong Tian is a professor at Peking University. He is also the dean of the School of Electronics and Computer Engineering. He's an active researcher in many fields like distributed machine learning, multimedia big data, and neuromorphic vision, which is the topic of his talk today. And I've been collaborating with Yonghong Tian and some of his students, in particular Wei Feng, for 2 years now, and this collaboration has been really fruitful. So Yonghong Tian, thanks a lot for having accepted our invitation. We know it's late in China, but we are all looking forward to your talk. You can start now.
Okay, thanks, Tim's introduction. Good afternoon and good evening, everyone and online friends. And in this talk, I will share our vision about spiking deep learning. And here, the SpikingJelly is one of the development frameworks that our team developed for the deep spiking neural network. So it's regarding as the second generation of neural networks, which use sequential and discrete spikes rather than float value to communicate between layers. Due to the spike trigger calculation mechanism, ANNs are even driven and can up to 1,000 times more power efficient than ANNs on neuromorphic chips. So uh, the so however, compared with the second generation of deep learning networks, the size and performance of current SNs are limited, as shown in this figure. Ah,
Yeah, Yonghong, you're not in slideshow mode.
Yeah.
You're in presenter mode, but not in slideshow mode. I don't know if
Okay.
It's not a big deal, but.
I'm sorry.
You can continue like that if you prefer.
Maybe re-share again.
No, I think you need to put your PowerPoint in slideshow, but it's not a big deal. I mean, if you. Or maybe, yeah. Were you still on the first slide, or you had moved? Because we only saw the first slide.
Yeah, I'm sorry. It's okay. I'm screen it.
Yeah, that's working.
Okay.
Yeah.
So let's start again. Oh, from here. Okay. However, compared with the second generation of deep learning networks, the size and performance of current SN are limited, and so as shown in this figure, due to the back propagation training algorithm and the deep learning network can achieve high performance. So on the other hand, if SNN is trained by heavy learning, HTTP, and other algorithms, it is difficult to realize deeper network optimization. Therefore, the lack of learning algorithms with both biological plausibility and computational efficiency has become the major bottleneck in SN studies. The SN learning challenge mainly comes from non-differentiable spike generation mechanism. From the equations, we can see the derivative of the spike file process cannot be used in the BP. So in this case, traditional learning rules, including Hubble learning and HTTP, can only solve simple learning tasks. For example, classifying the mixed dataset. To solve this challenge, two popular deep learning methods were proposed, including the secret gradient method and the ANN-to-SNN conversion. The secret gradient method still uses the BP algorithm for SN training, but the bank process uses another function similar to its gradient to replace it. Although this calculation is wrong, the extensive experiments show that the network can converge normally. Another method is ANN to SN method, which converts the trained SN to the corresponding SN through weight adjustment and normalization strategies. In general, the former needs less simulation time steps suitable for sequential data, while the latter needs more simulation time steps. So now let's back to 2019 winter. Spiking deep learning was attracting more and more attention, while most existing ASN frameworks are not designed for deep learning. In this case, researchers who want to combine advanced deep learning methods with ASNs have to build basic spiking neurons and synapses from scratch, which results in duplicated and uncoordinated efforts. Variable programming language, coding styles, and model definitions from different researchers cause troubles for reuse. Additionally, high-performance programs accelerated by GPU is not easy to write for most researchers. To promote the development of deep SNs, we developed an open source SN deep learning framework, SpikeJelly, from 2019. The overall of this framework, it's okay. The overall of the structure of SpikeJelly is shown in this figure. It supports to both circuit gradient learning and ANN-to-SNN methods. Popular neuromorphic datasets are also integrated in SpikeJelly, and neuromorphic chips such as Intel, Noihi, and Linxi from Tsinghua University team are also supported. The advantage of SpikeJelly includes flexible APIs and high performance, so widely used by the community. After being open sourced in December 2019, SpikeJelly has been widely used in many papers in the field of deep learning with SNs. Till now, there are more than 40 papers using SpikeJelly to develop their algorithms. First, let me introduce some basic concepts. In SpikeJelly, there are some delay in the screen. In the SpikeJelly, we use the activation-based representation of spikes. More specific, we regarded spikes as a specific activation whose value can only be 0 or 1. Compared with the activation in ANN, spikes have an additional time step dimension. Thus, in SpikeJelly, we have two data format, that is data in a single time step with shape n star and data in many time steps with shape t n star. Accordingly, modules in SpikeJelly have two-step modes. In the single-step mode, the module receives an output sync time step data, while in the multi-step mode, the module receives an output sequential data. Similar to ANN, spike neurons in essence are stateful. The output YT depends on not only the current input xt, but also the hidden state ht minus 1. In PyTorch, the hidden states are part of the inputs and outputs, while in SpikeJelly, hidden states are stored inside the module. This difference makes users build SNN easily because modules only have one input and one output, but we must reset the module before we input a new sample. It can be done easily by reset function. Here is an example. So using different steps modes will change the propagation pattern of the network. If all modules using the single step mode, the propagation pattern is step by step. For example, input x0, output y0, input x1, output y1, and so on. For the way how the computational graph is built, the step by step is deep's first search. Meanwhile, its memory consumption is irrelevant to T in inference, making it suitable for ANN-to-SNN inference with NADI T. If all modules use multiple step mode, the propagation pattern is layer by layer sequentially rather than data and a single time step is propagated across all layers. It builds the computational graph using both breadth first search. It is faster for training SNNs with BPTT, but its memory consumption is proportional to T, even in inference, indicating that we can only use layer by layer with larger T. So there are many containers in SpikeJelly, most of which are designed for simplifying the usage. When we employ ANN in multi-step mode, the for loop on the time-step dimension is inefficient because when inputting x0, x1, and so on, xt-1 to stateless modules, yt does not depend on xt-1. So we can use sequence to ANN container to avoid the unnecessary for in loop in the time steps. This container is used for warping ANN with in sequence. It will merge the time step dimension to batch dimension. Thus, the calculation on the time step dimension is parallel. We test on convert to D with different time steps and found that sequence to ANN container is much faster. In our ACCV 2021 paper, we built a general spiking neural mode. Now it is used as the best neural in SpikeJelly. We use 3 discrete time differential equations to describe a spike neural, which are charge, fire, and reset equations. To avoid confusion, we use HT to represent the membrane potential after charging but before firing, and VT to represent the membrane potential after resetting. Note that there are 2 kinds of reset, which are hard reset and soft reset. Hard reset, which resets VT to reset, is popular in directly training SNNs for its better performance in experiments, while soft reset, which subtracts weightage if the neural fails, is adapted in most SNNs converted from ANNs for its lower fitting error to remove activations. This base spike neural is designed to follow the 3 equations. So we only need to define the charge equation to get the new neuron. Here is an example of simulating the leaf neuron. Note that xt is the input and st is the output spike. For more smooth curve, we recut h start t, which include ht and vt. Considering that the spike neurons are the key module in essence, we have designed some acceleration methods for faster simulation. In general, the acceleration is based on fill-in operations. Fill-in operations into a single CUDA kernel amortize memory access time and kernel launch time. In the single-step mode, we use torch.git to fill simple point-wise operations. In SpikeJelly, most functions are decorated by torch.git. In the multi-step mode, SpikeJelly provides a CuPy backend for advanced acceleration. The multi-step forward and backward operations are fused into a single row CUDA kernel. So the fused kernel has extremely high efficiency, especially when T is very large. The CuPy kernel is created semi-automatically from the Python neuron. Here is an example. Parameters in the neuron are marked with different colors. Correspondingly, the CUDA codes controlled by these parameters are also highlighted with the same color. For example, the parameter decay input equals to false will disable two parameters in the code paragraphs. SpikeJelly provides flexible APIs for users to extend. Here is an example of defining the exponential integrate and fire that if neuron. By inheriting the base neuron, we only need to add the neural charge function, and then we will get the complete if neuron. Circuit learning is one of the most popular spiking deep learning methods, which is implemented by redefining the gradient of neural fire. In forward, we use theta x to generate spikes. Note that the derivative of theta x is impulse function delta x, which is infinite and x equals 0 and 0 otherwise. So we cannot use such a gradient to train our SNNs. Thus, researchers define a circuit function delta x, sigma x, which is a smooth approximation of theta x. In backward, we use sigma x derivative to redefine theta x derivative. This figure is the example of using sigmoid as the secant function. Another SN learning method is ANN-to-SNN. From the figure, we can see there is a strong correlation between the activation value of ReLU neurons in AN and the fire rate of IF neuron in SN. So based on the correlation, the ANN-to-SNN converter is implemented in SpikeJelly by replacing ReLU neurons with IF neurons, and various normalization methods such as the max norm, robust norm can be selected. Neuromorphic datasets are widely used in essence. In SpikeJelly, we have included these 5 datasets, and SpikeJelly also provides 2 kinds of interfaces. The first is the orange AER interface. Here is an example. By setting data type as event, we can read the original event in the format XYTP. And the second interface is the frame format, which returns a frame with shape TCHW. Here is an example of device gesture. SpikeJelly provides some downsampling function to slice the events and the interface and integrate each slices. This figure shows how this processing is implemented. The SpikeJelly has been built on an extra-scale AI supercomputer Ponzi Cloud Brain. Meanwhile, we also built a brain-like system using Lindsay chips. On this hardware and software platform, we also developed an open SN training and computing platform, including large-scale SN training algorithms, datasets, model room, and API. These slides show more details about the brain-like system, which utilizes the Lindsay neuromorphic chips K200 and HP300 card to build a brain-like server. Here is the system architecture, and there is the software toolkit. On this platform, our team have carried out extensive research works covering from neural level, the neural networks level, and large-scale computing and application level. In the following, I will share some of them with you. The leaf neural is the common used neural in essence. There are 2 kinds of parameters, including the synapse-related parameters such as W and the membrane potential-related parameters such as time constant tau. We have paid more attention to W in the past, but next to tau. Here, tau is also important for the representation of working memory and the formation of learning. We also performed several preliminary experiments. Here are the results. We can see that the adjustment of W and tau have different effects on neural dynamics. Here, similar tau and or larger W means faster response and attenuation. Moreover, increasing or decreasing tau will scratch the curve in the T direction, while increasing and decreasing W will scratch the curve in the V direction. So adjusting tau and model to learn the membrane time constants of SN. Compared with leaf neural, tau in the p-leaf neural is described by the fraction 1 over Ka, where Ka is the clamp function, and we use K equals to sigma mod A, where A is the learnable parameter. In most cases, we reset equals 0, then Ht can be expressed and this equation. We can find that Ka controls the balance between forget and remember, which plays a similar role as the gate in LSTM. That's using a learnable tau is reasonable. So in the p-leaf neural, tau is optimized during training and can be shared within a neurons in the same layer in essence. Of course, the performance of p-leaf neural is slightly better than leaf neural, which hyperparameter tau was in laboratory selected. Meanwhile, the PNF neuron achieves the short accuracy on 6 datasets, including 3 static datasets and 3 neuromorphic datasets. The PNF and SNNs are available in SpikeJelly. The next problem is how to formulate network from neurons. Biological research shows that the total brain volume of humans will reach approximately 90% of the adult value by age 5 or 6 years. Regional value change still continue as a result of ongoing plasticity of fine-tuning of neural systems. The varying structure in neural networks is refined throughout lifetime. On the microscopic scale, the variant refers to the evolution of network structure, but on the macroscopic scale, the variant is not explained as formation and elimination of dendritic spans. Dendritic spans are small membranous protrusions that arise from dendrites. It lies close to axon terminal and receive signals from nearby axons. Here, figure A illustrates the enlargement of spans, and B gives the shrinkage and pruning of spans. It is clear that growth and elimination of dendritic spans change variant structure. Moreover, span size is positively associated with synaptic weights. Inspired by the mechanism in brain rewiring, we propose gradient rewiring algorithm, namely grade R for short. At first, we parameterize weight use span parameters theta. In this way, the scene change of theta can be viewed as growth or pruning. The positive or negative weight correspond to excitatory or inhibitory synapse and are optimized separately. Secondly, the modeling growth rule mapping has a zero gradient when theta is negative. This is not designed since dendritic spans should always receive learning signal. Therefore, we redefine gradient and negative part as the same as when theta is zero. Finally, we introduce the speed control of pruning based on Bayesian pair to enhance the sparsity. So to sum up, the gradient rewiring explicitly model the growth and pruning of synapses. This is the experimental results. The figure shows the change of network performance and sparsity during the training process, where the solid line represent the network performance and the dotted line represents the connectivity. In general, the higher sparsity, the more the performance degrades. In extremely sparse scenarios, the performance loss is only about 3.5% when only 1.73% connection. In addition, there are two noteworthy results. First, the number of synapses reconnected by each epoch is close to number of synapses being pruned, even though the network sparsity is no longer increasing near the end of the training. That is, the two processes of pruning and growth are still ongoing. Secondly, the experiment found that there is a weak positive correlation between sparsity and the spike fire frequency, and the fire rate does not change significantly with the increase of the sparsity. The degradation problem is one of main problems when SN becomes deeper. ResNet is a well-known model to solve this problem in deep learning networks using the identity mapping. That is, if added layers implement in the identity mapping, a deeper model should have training error no greater than its general counterpart. By directly copying the similar design principle, SpikeResNet can also implement the identity mapping in forward. But in the backward, we found that its derivative is this. Consider that we often use the symbol like surrogate function. The gradient can hardly be 1 at both S superscript L brackets I equals to 0 and 1. We further analysis the gradient problem of SpikeResNet. Actually, when the identity mapping is directly implemented in SpikeResNet, we use many sequential blocks, then we will find that the SpikeResNet still suffers from the gradient vanishing or exploding problem. Here are 3 cases we observed on SpikeResNet 152 with different hyperparameters. To solve this problem, we propose a spike element-wise, we mean SEW ResNet, compared with the best block. SEW block skips the last SN and use the element-wise function G to connect outputs. Here we can use any of 3 operators in the network. When identity mapping is implemented, the gradient is 1, indicating that the SEW ResNet will never suffer from the gradient vanishing or exploding. Here show the experimental results on ImageNet. We can see that SEW ResNet can effectively solve the degradation problem. That is, the performance of SEW ResNet 152 is better than SEW ResNet 101 and then 50 and so on. Currently, we can utilize the SpikeJelly to train large-scale SNNs. We also provide the training script template online. In the next work, we will further utilize state transition of dendritic spans to enhance the sparsity of SNNs. There are 2 kinds of state transitions in neuroscience. The first is the transition between inhibitory and excitatory synapses. One might hear about the Day's law, which can be paraphrased as only one kind of neurotransmitters can be released from the same axon branch. However, recent studies have revealed that many neurons actually release different kinds of transmitters. So these figures illustrate the relation of the size of spans, transmitter types, and the connecting weight. We need to model such transition for more expensive power of SNN. The second one is transition between philopodia and mature spans. Philopodia can be viewed as a thinner span without bulbous head. Compared to mature spans, philopodia is too small to form connection to axon terminal and thus cannot deliver spikes. It is equivalent to no connection. So in general, philopodia is now considered as the precursor of mature spans and only the size can differ in effect. For this reason, we can model the growth and the pruning in SNNs by describing the span size. We thereby introduce the soft threshold mapping for describing relation between synaptic weight and span size, and model the state transition and abandon the renewal mapping in the previous work. We regulate the pruning speed by scheduling threshold. We also use the iterative shrinkage and thresholding algorithm for pruning when the magnitude of gradient is small. However, the soft threshold mapping also suffers from and zero gradient issue mentioned in the gradient R. So it can be avoided by modifying gradient to 0. The convergence after modification is given in our paper, and for learning, the gradient update is equivalent to solving a sparse optimization problem using a proximal gradient and L1 constraints. This work might be the first work of pruning that achieve no performance loss on large SN over ImageNet. It beats the current works by a large margin. We also pointed out that the threshold scheduler have strong influence on performance, which is very interesting and is still a pending question. Of course, we can also perform ANN-to-SNN learning on the framework. To do so, we first derive the equivalence condition between AN and SN by comparing the forms of the transformed AN and SN. Then we propose a key curve to measure the difference between their outputs and prove that the upper bound of K is this. And as a result, we can optimize the objective and upper bound of K simultaneously. Experimental results show that the conversion does not degrade network performance while reducing the inference time and energy consumption. Actually, the best practice of SNNs is neuromorphic vision, which is originally derived the concept of neuromorphic engineer proposed by Karamet in 1990. There are two kinds of neuromorphic cameras, that is the event camera such as DVS and the spike camera, which are mimicking peripheral retina and fovea, respectively. They are different.
Yonghong, sorry to interrupt. Just in about 5 minutes, we have to start the next talk. So if you want to leave room for questions, you should conclude soon, if possible.
Okay. I to question firstly. So for this, we have neuromorphic visual construction, and so we also do some work. And for the time, we give more details, and there are some demos. And finally, I think there are many open issues for learning ACM. For example, how to perform both biological plausibility and computational efficiency, and also how to both globally and locally efficient. Okay, thank you. I'm sorry, for example, networking problem, and so. Any question?
Yeah, so we can you hear me?
I can see there's some problem in the
So we had a couple of questions. So the most voted question is an easy one. Why is it called SpikingJelly?
Yeah. It's a good question. The term jelly may be jellyfish. It is inspired by the fact that the shape of jellyfish resembles a spike neural with detailed structure. So we refer it as SpikeJelly. Thank you.
Okay, okay. Another question by Laurent Perinet is SpikingJelly taking advantage with respect to the PyTorch backend that spikes are binary? It seems that as of today, quantized convolutions are still quite experimental.
So it's a good question. For now, only a few quantized operations are supported by GPU and CUDA, and I think most GPUs only support 8 bits operations or higher precisions. So for this reason, we still employ the full operation on GPUs. I think maybe this problem may be solved with some neuromorphic chips in the future.
Okay, and then when we have another question by Julian Rosbroich. Oops. Can the current framework take advantage of sparse activity? It's a similar question, I guess. For example, by using sparse matrix multiplication or event-based propagation in forward or backward pass.
Okay, thank you. I think this is a good question. Not yet. Event-based computing paradigm is now considered efficient only on neuromorphic chips. I think sparse matrix modification is not RIP enough and also experimental in most deep learning framework. So it also requires extremely high sparsity to accelerate computing, which I think still lead to bad performance now. Okay.
Okay, thanks. And maybe a last question by Dengyu Wu. The container is an excellent idea for training SNN, but it seems that SpikingJelly is still based on PyTorch. Will it be extended to TensorFlow or JAX? Or if any license permission needed for other developers to implement the container in their code?
Okay, it's a good suggestion. Indeed, SpikeJelly does not support JAX for the time being, but it allows developers to and by themselves. I think anyone is welcome to join us. In addition, some articles use our container in their own code, and they also set our framework. So we think this is a good phenomenon. So I think welcome many more developers to join us, the SpikeJelly community. Thank you.
Okay, well, I think we have to go to the next talk, but thanks a lot, Yonghong. It was a very good talk.
Thank you. I'm sorry again.
See you in the next room.
Bye-bye.
Bye-bye. Don't worry, we are right on time.